In a dramatic turn of events, the European Organization for Nuclear Research, CERN, announced the unexpected shutdown of the Large Hadron Collider, LHC, the world's most powerful particle accelerator. While routine maintenance is common for this colossal machine, the abrupt halt hints at a more significant development. What could have been unearthed in the depths of the LHC? Is it a gateway to new dimensions or a harbinger of unforeseen dangers? Join us as we reveal the intriguing findings at CERN before it shut down. CERN, the European Council for Nuclear Research, has been making headlines since the 1950s with its groundbreaking experiments. While it has received much praise, it has also sparked concerns about creating black holes or altering reality itself. One of its most significant and controversial achievements is the construction of the LHC. The LHC is not something most people encounter in their daily lives, so it's understandable that many have never heard of it. However, this machine is like a time machine, offering us a glimpse into the very fabric of the universe. It is a marvel of human innovation, a massive ring measuring 17 miles in circumference and buried 175 meters beneath the Earth's surface. Remarkably, it spans 2 countries, running beneath both France and Switzerland. This impressive machine, with its $4.5 billion price tag, is the centerpiece of CERN's experiments. Over the years, even more money has been spent on upgrades and maintenance, which has paid off significantly by revealing secrets of the universe. But how does it work? The LHC accelerates particles around its loop until they are moving near the speed of light, completing thousands of laps every second. This is achieved using electromagnets that generate a magnetic field 1,000 times stronger than Earth's own. However, there are concerns about the impact of such a strong magnetic field on nearby electronics and the planet's magnetic balance. Once the particles reach their top speed, they collide head-on, creating powerful collisions akin to cosmic crashes. These collisions release massive bursts of energy and a variety of particles. When these particles collide, they shoot off in all directions, but most vanish almost instantly. The exciting part is that by changing the types of particles they collide, scientists can discover new particles hidden in the chaos. To capture these fleeting moments, super-sensitive detectors are positioned around the collision sites. These detectors act like cosmic cameras, capturing every detail of the collisions. The data generated is immense, amounting to over 15 petabytes each year, equivalent to a vast library of information. Analyzing this data requires significant time and effort. But within this treasure trove lie the answers to some of the universe's biggest mysteries. One of the remarkable achievements of the LHC is challenging the standard model. But why should you care about this model? Think of it as a guidebook for the universe, explaining how particles and forces interact, like instructions for building a Lego set. It covers everything from tiny particles like quarks and leptons to the forces that hold them together. Quarks come in 6 different types, each with its own electric charge and mass. Then there are the leptons, such as electrons and muons, which play a crucial role in forming atoms. And let's not forget about the bosons, which are the messengers of forces like electromagnetism and the strong force that holds quarks together. However, despite its power, the standard model isn't perfect. It leaves some big questions unanswered. That's where the LHC comes in. With its powerful collisions, it's uncovering mysteries that the standard model can't explain. Take the beauty quark, for example. It's challenging our understanding of the universe in unexpected ways. Scientists discovered that when beauty quarks break down, they don't follow the rules set by the standard model. According to predictions, these quarks should transform into muons and electrons at similar rates. However, experiments at the LHC showed something different. This unexpected twist suggests there might be unknown particles or forces at play, challenging our understanding of the universe. And that's not all. The LHC's particle collisions sometimes produce bizarre particles that the standard model can't explain. Take the pentaquark, for instance. It's a new kind of particle made up of 5 quarks instead of the usual 3 found in protons and neutrons. This discovery opens up a whole new realm of possibilities, hinting at other quark combinations waiting to be discovered. What's really exciting is what this means for our understanding of the universe. The LHC is revealing new aspects of particle physics that could lead to a deeper understanding of the fundamental nature of reality. The pentaquark suggests that there are mysterious forces at the subatomic level that we are just starting to understand. Discovering it is like finding a hidden rule book that has been guiding us all along, just waiting for us to notice it. The discovery of the pentaquark was incredible, with a statistical deviation of 15, showing just how accurate and powerful the LHC is. In particle physics, a deviation of 5 is the gold standard for proving a particle's existence, so 15 is extraordinary. The LHC didn't stop there. It also discovered the tetraquark, another unusual particle that challenges the standard model. This particle, named TCC+, has 4 quarks, 2 heavy charm quarks and 2 lighter ones, all held together by the strong nuclear force. Just like the pentaquark, its discovery hints that there may be even more quark combinations waiting to be found. The LHC also made another startling discovery. The Higgs boson, a particle crucial to our understanding of the universe, is heavier than we first thought. The Higgs boson, sometimes called the Higgs particle, is a fundamental part of the standard model of particle physics. It's created when the Higgs field, a basic field in particle physics theory, gets excited through a process called quantum excitation. In this model, the Higgs boson is a heavyweight champ. It's a type of particle called a scalar boson, with no spin, no electric charge, and no color charge. But it isn't very stable and tends to break down into other particles as soon as it is formed. The Higgs field is like a cosmic carpet spread throughout the universe. It always has a non-zero value, even in empty space, giving mass to all sorts of particles through the Higgs mechanism. It's like the Higgs field throws a party, inviting all the particles to join in, giving them their mass and breaking a cosmic symmetry in the process. We owe this insight to physicist Peter Higgs, who, along with a team of scientists, proposed the Higgs mechanism back in 1964. This groundbreaking theory explains how particles gain mass and led to the prediction of the Higgs boson. It was like putting together a puzzle. If their ideas were right, there had to be a particle out there with certain properties, and the Higgs boson confirmed it all. The Higgs boson, often dubbed the God particle, was discovered after a 40-year search. In 2012, scientists finally struck gold using the powerful ATLAS and CMS experiments at the LHC. They found a particle that fit the long-sought properties of the Higgs boson. This discovery was like finding the missing piece of a cosmic jigsaw puzzle. The breakthrough was so significant that the 2 key theorists, Peter Higgs and François Englert, received the Nobel Prize in Physics in 2013. However, it's crucial to recognize that this milestone was achieved through decades of effort and collaboration among many scientists. Between 1960 and 1972, several researchers independently contributed to the foundational theory known as the Higgs mechanism. Fast forward to recent years, as the LHC continued its work and collected more data, scientists took a closer look at the Higgs boson and made a surprising discovery. Its mass is greater than 125 giga-electron-volts, GeV. This revelation caused quite a stir, because if the Higgs boson is indeed heavier than predicted, it could mean rethinking some fundamental aspects of our understanding of the universe. Does this mean we need to discard the standard model and start over? Not necessarily. However, it does suggest the exciting possibility of new particles or forces beyond our current knowledge. This discovery adds another piece to the puzzle, potentially altering how we perceive the universe. The discovery of the heavier Higgs boson has reignited interest in the Higgs field and its role in shaping the universe. Even after the initial discovery, research on this mysterious particle has continued. As we look forward, the investigation into the Higgs boson is expected to intensify, particularly during the LHC's third cycle. This will be especially true after the completion of the particle accelerator's high luminosity upgrade in 2029. This upgrade will allow the LHC to perform more collisions, giving researchers more chances to uncover unusual phenomena that deviate from the standard model of particle physics. CERN estimates that each year following the upgrade, the LHC will produce about 15 million Higgs bosons, a significant increase from the 3 million created in 2017. This surge in production could help identify various forms of the Higgs boson beyond the standard model. Some theories propose up to 5 different types of Higgs bosons, with some being rarer than the fundamental Higgs. Even before these advancements, scientists found compelling evidence of a magnetic Higgs boson. But why is the Higgs boson so important? The Higgs field is vital in shaping the universe, particularly in its early stages. It defines the properties of the vacuum in our spacetime, leading to the existence of matter interactions and the emergence of mass in all fundamental particles. Without the Higgs field and the Higgs boson, the cosmos would lack atomic elements, stars, and even life itself. So why is the Higgs boson often called the God particle? This nickname gained popularity after the release of a book titled The God Particle by Nobel laureate Leon Lederman. He intended to highlight the Higgs boson's critical role in understanding why particles have mass. The term God particle is somewhat controversial in the scientific community, as it might suggest a religious connotation, which was not Lederman's intent. Nonetheless, it underscores the significance of the Higgs boson in the realm of particle physics and its fundamental importance in the universe. However, despite the groundbreaking discoveries at CERN, the shutdown of the LHC was a shock to the scientific community. The shutdown, while temporary, left scientists and enthusiasts speculating about the reasons behind it. What could have been discovered that warranted such an abrupt halt? Could it be a potential danger or an unprecedented breakthrough? The announcement from CERN was succinct, stating that the LHC would be temporarily closed for unscheduled maintenance and upgrades. While routine maintenance is a regular occurrence, the timing and nature of this shutdown fueled various theories. Some speculated about the discovery of new particles that could alter our understanding of physics, while others feared potential hazards, such as the creation of miniature black holes or the disruption of space-time. Among the many theories, one stands out: the possibility of new dimensions. Theoretical physicists have long speculated about the existence of dimensions beyond the familiar three-dimensional space and time. The LHC's experiments have the potential to uncover evidence of these extra dimensions, which could revolutionize our understanding of the universe. The detection of particles disappearing into or emerging from other dimensions would be a monumental discovery, opening up entirely new realms of physics and cosmology. Another intriguing theory revolves around dark matter. Despite being an essential component of the universe, accounting for about 27% of its mass energy content, dark matter remains elusive. It does not emit, absorb, or reflect light, making it invisible and detectable only through its gravitational effects. Scientists hope that the LHC might produce dark matter particles, providing insights into this mysterious substance that shapes galaxies and influences cosmic evolution. The shutdown also raised concerns about potential dangers. One of the most common fears is the creation of miniature black holes. According to some theories, high-energy particle collisions could produce tiny black holes, which might grow and pose a threat to Earth. However, most physicists believe that these black holes would be incredibly small and decay almost instantly, posing no real danger. Nevertheless, the idea has fueled numerous discussions and debates. CERN has assured the public that the LHC's experiments are safe and that the organization follows stringent safety protocols. The safety of particle collision experiments has been extensively studied, and the consensus among scientists is that the risks are minimal. The energy levels achieved in the LHC, while immense by human standards, are still far below the natural cosmic rays that constantly bombard Earth without causing harm. In conclusion, the shutdown of the LHC at CERN has sparked widespread curiosity and speculation. Whether it is a routine maintenance procedure or the precursor to a groundbreaking discovery, the world is eagerly awaiting the next chapter in this scientific saga. The LHC has already revolutionized our understanding of the universe, and its future holds the promise of even more astonishing revelations. As we stand on the brink of new discoveries, we are reminded of the profound words of physicist Richard Feynman. I think nature's imagination is so much greater than man's. She's never going to let us relax. The mysteries of the universe continue to unfold, and with each discovery, we inch closer to understanding the true nature of reality.